Lesson 41. Okay, systems of equations again. Well, now that you've paid your dues, so to speak, learning to solve systems of equation, remember doing 2 by 2s by graphing, 2 by 2s by substitution, 2 by 2s by addition, 3 by 3s by extracting a 2 by 2, 39 Kramer's rule, 40 the Gaussian elimination thing, and setting up augmented matrices. Now this was good to see, because you saw that it is possible to set up an augmented matrix as large as you want, and you'd be able to write a computer program to solve it. Today, we'll use the computer to solve our systems. You've paid your dues, you've learned how to solve them by hand, now let's use the computer. So what's left to learn? Well, what's left to learn, of course, is how to set up the systems in the first place. Where do these equations come from? We've kind of didn't even mention that this whole time. But it turns out that setting up and solving systems of equations is a big part of a lot of science and engineering work, which I'm going to try to kind of get you a glimpse of that today, though I'm going to have to start contrived. You have to start with contrived examples because they're easier to understand, and then you can sort of learn the approach. And then I'll just kind of push us towards some real applications as we go. So here we go. I got 5 examples, and I'm going to go in order from the most contrived to the least contrived. This one's contrived. Why am I calling this one contrived? I'm calling it contrived because, look, hey, I got pennies, nickels, dimes, and quarters. How many of each kind do I have? You think they'd pay an engineer to do that? You're wrong. But it's a good example to learn on. So let's see. How does this work? How does this work? First of all, notice we've got 4 things we're trying to solve for. We're trying to figure out pennies, nickels, dimes, quarters, how many of each? That's what we want to know. How many pennies, how many nickels, how many dimes, how many quarters? So the first thing we should always do, and I'm doing this before I even read the rest of the problem, step 1 is always declare your variables. And you kind of want to do this a little bit carefully. I'll put an exclamation point. You kind of want to do this carefully. Like, for example, you could use X, Y, Z. Actually, I'm going to use P, N, D, and Q, I think would be a little more natural. So P is the number of pennies. See, I'm trying to be specific here. I'm not going to write just P equals pennies, because somebody might not know what I mean. Did you mean the number of pennies? Did you mean how much money you have in pennies? What did you mean there? So try to spell it out as best you can. Don't make me guess what you meant. So P is the number of pennies. I'll use N as the number of nickels. I'll use D as the number of dimes. I'll use Q as the number of quarters, because that's what they asked us to solve for. So how many of each coin do we have? So we're going to solve for P, N, D, and Q. Now, as a little aside here, if we've got 4 unknowns, that tells us something right away. It tells us that we're going to need 4 equations. Right? Remember, all of these systems we solved for, they've always been sort of like square, like a 2 by 2. 2 equations, 2 unknowns. We did 3 by 3s. 3 equations, 3 unknowns. If you got 4 equations, or if you've got 4 unknowns, you're going to need 4 equations. And so on. You need an equal number of equations as unknowns. So we're going to need 4 equations. That means we're going to need 4 clues. And happily, that's what they do. They give us 4 separate clues. So translate the clues into equations. That would be our next order of business. So clue A says 83 coins altogether. 83 coins altogether. Well, that's counting the coins. And that's what these variables do, right? P counts how many pennies, and N counts how many nickels, and D counts how many quarters. So this is actually kind of a nice equation. We can just say the number of pennies and the number of nickels and the number of dimes and the number of quarters all adds up to 83. Woohoo! That's our first equation. Notice this equation is completely ready to be coded into an augmented matrix, right? Put your coefficients of your P, N, D, and Q there. You'd have a line, and then you'd have the 83 on the other side. We are on our way. Let's look at the next clue. B. Total value 907. Total value $9.07. Okay, What is wrong with this picture? The total value of the pennies, nickels, dimes, and quarters is $9.07. Well, there's a couple things wrong with this picture. First of all, you just said that P, N, D, and Q add up to 83. So what do you mean they also add up to 9? They can't add up to two different things. So you're contradicting yourself if you say this. But even more seriously than that is that P is not how much the pennies is worth, right? I was being very careful about that up here. P is not what the pennies are worth. P is how many pennies you have. Well, what are the pennies worth? Trying to make a blue pen here. Come on, you. Okay, the pennies are worth $0.01 each. So if you want to know the value in dollars, because that's a $9, if you want to know the value in dollars, you take the number of pennies, multiply it by 0.01. You want to know the value of your nickels? You take the number of nickels and you multiply them by $0.05 each. You want to know the value of your dimes? You take the number of dimes and multiply them by 0.10 each. And so on for the quarters. So you take 0.25 times the number of quarters, that gives you the dollar value of the quarters. That adds up to 907. And that's our equation too. And you know what? Why don't we just code? We might as well keep coding this matrix over here. I like this. Let's build it as we go here. So I can put the 0.01 coefficient of P here. So sometimes I do this just as a reminder to myself. I kind of helps me remember what the columns all stand for. So these are the coefficients of P, coefficients of N, coefficients of D, coefficients of Q. So coefficient of N is 0.05, that would go in the second column. Coefficient of D is 0.10, goes in the third column. Coefficient of Q is 0.25, goes there. Across the equals is a $9.07. Wow, 2 equations, 2 to go. Well, they gave us another clue. Let's go get it. What did it say? This one says, twice as many dimes as quarters. Okay. Twice as many dimes as quarters. Put that in quotes, that's the clue. There are twice as many dimes as quarters. Now, one way you might think of this is say, and the other way you might think of it is this way. Now they can't both be right, so you have to figure out, is it this one or is it this one? Which one of those two little equations has the same meaning as this little English phrase here? Well, I hope you choose that one. Twice as many dimes as quarters. Okay, you don't want to quite do this, twice as many dimes. You know, it doesn't quite work like that. I usually think it through like this. I say, well, do I have more dimes or do I have more quarters? Well, I have twice as many dimes. I have more dimes. Well, if I have more dimes, which is the bigger number, the D or the Q? If I have more dimes, dimes is bigger than Q, right? Well, in this equation, dimes will be bigger than Q, because whatever Q is, you're going to double it, and dimes will be bigger. And notice that's not what's going to happen in this equation, right? So it is this equation here. So cross that one off. That ain't it. That ain't it. So it's D equals 2 times Q. Now, because we want to code it, let me switch colors again. Because we want to sort of code it into the matrix, what we should do is we should subtract the 2Q on both sides and have it equal 0. Now, what are our coefficients here? Well, we don't have any pennies, so that's kind of like having a 0 times the number of pennies. We don't have any nickels, so that's kind of like having a 0 times the number of nickels. This is a 1 times the number of dimes. This is a minus 2 times the number of quarters, and then on the other side we've got a 0. Okay, we're on our way. One more clue and we'll have our system. So, what's our other clue? One more quarter than nickels. One more quarter than nickels. I invite you to pause for a moment, see if you can write that equation. If you can correctly express this idea that you have one more quarter than nickels, what does that look like? And I'll try to code it right into our matrix up there too. Pause. Come back. Okay. One more quarter than nickels. Well, again, which is bigger, the quarters or the nickels? Got one more quarter. The quarters is bigger. This is the bigger number. The quarters has to be bigger than nickels. So whatever nickels is, I'm going to have to add 1 to that to make it as big as the quarters. That's one way you might look at this. Another way you might look at this, if you like playing with words, 1 more quarter than nickels really means that the number of quarters is 1 more than number of nickels. That's kind of rephrasing it. It means the same thing, right? If you have 1 more quarter than nickels, then the number of quarters you have is 1 more than the number of nickels. And this, you really can sort of translate. Quarters is. 1 more than means to add 1 to the number of nickels. And that's the same equation as I had over here. Okay, so you got to find a way that's really comfortable to you, that makes sense to you. So anyway, the Q is the n plus 1 is what I want to say here. And what we're going to do is we're going to subtract the n on both sides. That way all our variables are on the left and we have a constant on the right. And now we want to code our matrix. What if we got times the number of pennies? Nothing. What if we got times the number of nickels? A -1. What if we got times the number of dimes? Nothing. What if we got times the number of quarters? 1. What's the number on the right? 1. Okay. There is our matrix. Let's get into a different color here, folks. Let's use this one. There is the matrix that we need to solve. Now, you did have a homework where you would have solved that by hand, but let's not do that again. Let's do this. Write this down. This is a nice website. https://online mschool. That's all one word. I have no idea who these people are. But onlinem/math/assistance/equation/ and they didn't spell Gauss right. They only used 1 S. Shame on them. But if you do that, if you spell that, you will come to a nice matrix solver. Now I think I can do that with this here Notability software. So let's, where is this? Web clip. Let's try this. Yeah, go to Safari. Let's do this. We're there, I think. In fact, here it is right there. It's this tab. There it is. Online mSchool. I should probably scrunch a little. It says Gaussian elimination calculator. Oh, I guess I don't have my I don't have my pen anymore. But if you scroll down to here, you'll see that, oh, look, you can pick how many equations you want. I want to have 4 equations, 4 unknowns. So you set it like that. Now they're going to use x1, x2, x3, x4, but that's okay. Just put the numbers in the same order as they're in the matrix. So we've got a 1 here. How am I supposed to type a 1? What am I supposed to do? Like draw a 1? Did that work? That worked. I got a 1 here. Wait a minute, that's not a 1. That's an exclamation point. What are you doing to me? I want a 1. Is that a 1 or is that an I? Where's my keyboard? Give me the keyboard. All right, no, I want numbers. Okay, here we go. This, come on. This is supposed to be a 1. Thank you. This is supposed to be a 1. This is supposed to be a 1. This is supposed to be a 1. This is supposed to be an 83. Cool. This is, what'd you do? This is supposed to be a 0.01. This one is supposed to be a 0.05. No, not a 0t. What are you doing to me? 0.5, right? Okay. This is supposed to be a 0.10, which I can enter as 0.1. This is supposed to be a 0.25. Let's see what it does here. 0.25. Okay, and then, why is that an 8e? That was supposed to be an 83. What in the world goes on with this? Anyway, and then down here, this is supposed to be a 9.07. 9.07. Apparently if you type a 0, it'll let you type another number. This is a 0. Actually, I should have left it there. That's a 0. This is supposed to be a 1. This is supposed to be a -2. Let's hope it lets me do that. -2. Ooh, beauty. And then that's supposed to stay a 0. That's supposed to stay a 0. This is supposed to be a -1. That's a 0. This is supposed to be a 1. And this is supposed to be a 1. Moment of truth. Did I type this all correctly? So I hit the solve the system, and you scroll down, you scroll down, you scroll down, and you look at that. Look at that. Right there. See, it even makes a check, and then it gives you the answer again. It gives you the answer twice. What could be better? So when it says x1, x2, x3, x4, that's just going across your matrix in the same order. We had P, N, D, Q. So that's saying P equals 12, N equals 17, D equals 36, Q equals 18. How do I get back to notability? Go back to notability. Yay! So I hope you had fun there. That was great, right? So that is a nice website. That website will do up to a 6x6 for you. So anyway, let me write down our solutions. We got the first variable was 12. The first variable was P. The next variable was 17. The D came out to 36, and the quotas came out to 18, and that's our answer. So now, see, you want to do the homework just so you can use that solver, right? Just so you can plug it in and go, wow. But the work, of course, is going to be to actually set up your systems of equations first. So this was pretty good. This is, again, it's contrived. It's not like you're going to get paid by somebody to do this for a job or anything. But it shows you how you can interpret language, so to speak, into algebra equations, and then you put them all together in a nice collection, gather them up as an augmented matrix, type it in, get your solution, then you're done. Okay, 1 down, 4 to go. These might get quicker because I won't have to explain as much. So who is this guy? Dr. Barney. He's inventing a new diet. He calls it the EBO diet because all you ever eat is eggs, broccoli, oatmeal. The eggs, broccoli, oatmeal diet. Sounds good. So let's see now here. Being a good doctor, Barney would like to calculate the number of servings of each that one should eat because you're supposed to get, according to Google anyway, 300 grams of carb every day, 200 grams of protein every day, 60 grams of fat every day. So you want to make sure you're getting your minimum, number of your macronutrients or whatever those are called. So, you don't want to give somebody a diet that's going to screw them up that bad, right? So okay. Here's the thing. Oatmeal, eggs, broccoli. Now I looked this up on the web too. A half cup of oatmeal has 12.6 grams of carb, 1.2 grams of fat, 3 grams of protein. An egg has about 0.6 grams of carb, 5.3 grams of fat, 6.3 grams of protein. Half cup of broccoli has about 3.9 grams of carb, 0.3 grams of fat, 2.3 grams of protein. Okay, that's cool. Very cool. Now, is there a way that we could eat a certain amount of this, a certain amount of this, a certain amount of this, and actually end up with 300 grams of carb, 200 grams of protein, 60 grams of fat? Well, if there is, we'll be able to solve a 3x3 system of equation, and it'll have an answer. Not guaranteeing it's going to have an answer, but it should have an answer. So, how do we do this then? Declare your variables. That's the first thing. What we're trying to figure out is how many servings of each. How many servings of oatmeal, how many servings of eggs, and how many servings of broccoli. So let's have, I think I will stick with X, Y, Z. O, E, and B sound weird to me. So anyway, let's stick with X, Y, and Z. So X will be the number of servings of oatmeal, where each serving is a half a cup. Y will be basically the number of eggs. I assume a serving of egg is 1 egg. And then Z is going to be the number of servings of broccoli, where a serving of broccoli is defined as a half cup. Okay, them's my variables. Now, translate the clues into the equations. Well, one of the clues is you need to have 300 grams of carb. Okay, 300 grams of carb. Where are you going to get your carb? Well, you're going to get your carb by eating oatmeal, eggs, and broccoli. Will all get you carbs. How much do you get from the oatmeal? 12.6 grams per serving. 12.6 grams for every serving of oatmeal. And you get 0.6 grams for every serving of eggs, or for every egg. And then you get 3.9 grams for every serving of broccoli, which we're using a Z. You're supposed to get 300 grams, it says. 300 grams of carb. There's our equation. Actually, these are coming together nicely, aren't they? Now, the fat, we're supposed to have, I think it said 60. 60 grams of fat. Let's do that one next. 60 grams of fat. So that means you're going to have 1.2 grams. I'm reading from these numbers now. For every serving of oatmeal, you're going to get 5.3 grams of fat. From every serving of eggs, you're going to get 0.3 grams from every serving of broccoli, and you're trying to get 60. And our third clue was the protein. 200 grams protein. Here's where you get your protein. You get 3 grams from every serving of oatmeal, and then you get 6.3 grams from every egg, and then you get 2.3 grams from every serving of broccoli, and we're trying to get 200 grams. Awesome. Well, you almost don't even need to write the augmented matrix, do you? You can see the augmented matrix here, right? I'll put it in quotes. So anyway, go to online M server, plug these in, see what you get. I'm not going to go there again. I'm just going to show you what I got. So what I got was, X was, and this was kind of funny, it gave me fractions, 21300 over 5341. Y equals 36600 over 5341. Imagine doing that as homework. Z equals 336400 over 5341. And of course I had to make decimals out of these to try to understand them. So X comes out to just about, if you round to one decimal place, 4.1 servings. And remember, X was the oatmeal. You should have oatmeal 4 times a day. Eggs. This came out to about 6.9. So what do you say? 7 eggs a day? So 4 servings of oatmeal, 7 eggs, and this comes out to 63 servings of broccoli. And I think a serving was a half cup. Let me look up here. Half cup. Spelled broccoli really bad. Half cup. So that's like, almost 31 and a half cups of broccoli. Man, that's a lot of broccoli. Well, I mean, if this is what you want to eat oatmeal, eggs, and broccoli, and if this is what you want here, you want to have 300 carbs, 60 fat, 200 protein, then this is the answer. Have 4 servings of oatmeal, 7 eggs a day, and 63 servings of broccoli. It's not taking into account all kinds of micronutrients like your calcium, potassium, and whatever else, but it would get you the macro, so to speak. The carbs, the fat, and the protein would all balance out. You want to try the EBO diet? You could. Now, this might seem like a nice, important example because, look, it's nutrition, right? Nutrition's important application, I would think, of math. I bet you there's people that do something like this in nutrition. At the same time, it's kind of contrived. Why would I say that this was a contrived example? Can you think of a reason? Well, one thing that makes it really contrived is since we've only got 3 things to balance here, to add up here, we can only have 3 equations. And if we only have 3 equations, we can only have 3 unknowns, which means you can only eat 3 things. You might pick different things, but you could only eat 3 things to solve this kind of a system. So that's not realistic, is it? No, it's not realistic. The other thing is I tried plugging different foods together, and sometimes I'd get you had to have -3 servings of this and -2 servings of that. So sometimes the answers you get don't even really work. They're not really practical. So, but it's a cool example though, ain't it? There'll be a couple like this in the homework that have nice solutions and stuff, but just as a PS, really you'd do a thing, because again, we only have three things that we can write equations for. So if you want more unknowns, you want to have how much blueberries am I going to eat or whatever, really you do a thing called linear programming. And since it's completely beyond the scope of this class, if you want to ask me about it, you can ask me about it, but linear programming would let you bring in more variables even though you've only got three things that you can add up, because you're allowed to use constraints like greater than, less than, and so on. So anyway, but I'm getting closer to real examples, right? Closer. Okay, now I'm going to get even closer. In fact, this is there. We're there now. This is a real example. I've done this myself. I've helped students who needed to do this themselves. This is real. So you're a technician of some sort, and you got some kind of a device that you're using to measure whatever, and you have to calibrate the device. Maybe it controls the temperature of your fish tank. I don't know what it does. But you have to calibrate your device. And this means that you have to find an equation that goes through all these points. Find an equation that goes through all these points, and then you would use that equation to help program your device to do what it's supposed to do. So let's abstract away from all of that and just say our mission is find an equation that goes through all of these points. Now, just as an aside, you might be thinking, gee, wouldn't I just fit a straight line? Well, you might want to fit a straight line if you knew that this point was maybe a little uncertain, this was a little uncertain. In other words, your measurements were maybe a little off. Then the idea of fitting a straight line is you're trying to average out all the errors in your measurements and get a nice straight line and say, yeah, it's got to be just about there. On the other hand, if you took your measurements and you said, no, this is a really good measurement, and so is this, and so is this, and so is this, these are accurate, then you'd say, look, I want an equation that goes, and I really do mean goes through these points. I need that. So it turns out that what you're trying to do is put a cubic polynomial through this to justify this. If you have 2 points, you can make a line, right? That would be called a first degree polynomial. If you had 3 points, you should be able to fit a parabola to it, which is like an x squared kind of a thing. Parabolas are x squared kind of a things. So 2 points makes a line, 3 points makes a parabola. We got 4 points. So if you got 4 points, you're going to need an x cubed plus a bx squared plus a cx plus a d. So every extra wiggle, you have to add a degree to your polynomial, just in case you ever have to do this yourself. So let's figure this out. How are we going to get what we need is the coefficients here, right? We need to figure out what times x cubed, what times x squared, what times x, and what's this number over here? We have to figure out these 4 numbers. And we can do that because we have 4 clues in the form of we have 4 points. We have the coordinates of 4 points that we want to go through. So we can get 4 equations, 4 unknowns. And this will be pretty cool, actually. So watch this. First, I'm going to say this. I'm going to rewrite the equation. I'm going to put the ax cubed plus the bx squared plus the cx plus the d on the left and say that equals y. And that'll help us get ready to write our augmented matrix, right? So we'll have coefficients. We'll have a, b, c, d, and then on the other side we'll have whatever y is over here. So how do we use this clue? Well, this is the point. Let's read the coordinates off that. Looks like x is -3. Looks like y is -2. Well, if you want this equation to work for that point, that means that when you plug in x equals -3 here, here, and here, you should get y equals -2. The a, b, c, d, we don't know what those are, but that's okay. We know that when we plug in x equals -3, right there, Negative 3, and then you cube it, you get a negative 27 times the a. I plug in the negative 3 here, squared, it's a 9, so plus 9b. I plug in the negative 3 here, so minus 3c plus d equals, and I'm supposed to get y equals negative 2. And that's my first equation. Boom. So I'm actually taking the coordinates and the point, and I'm saying, well, if that equation works for that point, then I should be able to just plug the x and y in, and that equation's supposed to work. Here's another point. X is negative 1, it looks like. Y is negative 1, it looks like. So again, what are we doing? We're plugging in x equals negative 1. So you cube it, you get a negative 1, so that's a negative a. We're plugging in x equals negative 1 here, and when you square it, you get a positive 1, so that's a 1 times b. We're plugging in x equals negative 1 here, so that'll get us a negative 1 times c, and that's a d. And then we're plugging in y over here, and y is negative 1, and there's our equation 2. Cool. Get this out of here, get this out of here, get this out of here. Next point. Now, let me get that out. The coordinates of that point looks like about x is 1. It looks like y is like negative half. So, okay, here we go for this point. Plug in x equals 1. Plug it in here, here, and here. So what we get is 1 cubed is 1 times a, plus 1 squared is 1 times b, plus 1 is 1 times c, plus the d equals, and then you grab the y and you put that over here. So the y is negative, I'm going to put a decimal, negative 0.5. 3 equations down, 1 to go. So what's the other point? This one looks like a 1, 2, 3, looks like a 4, 1. And so that means I plug in x equals 4 here. 4 cubed, is that a 4? 1, 2, 3, 4. Yeah, that's a 4. Okay, so when I plug in 4 there, 4 cubed is 64, so that's a 64 times a. Then I plug the 4 in here and square it, it's a 16, so it's a 16 times a b. I plug the 4 in here and multiply it by c, so that's a 4 times c. And notice it's always just plus d equals, and now I take the y, which is 1, and I put it over here. And now I've got 4 equations, 4 unknowns. Now, and here we are at desmos.com, where I have, you can see line 1 on the left, I've entered the equation of this cubic. Lines 2, 3, 4, and 5, I actually entered the coordinates of the points we were trying to go through. And when you look at the graph, you say, oh, look at that. It goes right through the points. Right through them. So we know that it worked. Okay, back to Notability. All right, that was that example. Okay, this one is another real example. It's so real that I actually teach this to our construction electricians. This is an electric circuit, and we're going to solve for the currents, which is the flow of electrons basically through this thing. Now before we do this, I should probably explain a little bit. This thing here is a battery. It's a 12-volt battery, and what it does is it pumps juice out. The negative terminal, that's the positive terminal, that would be the negative terminal. Electrons flow out in a stream that we call current, electric current, measured in amps. But anyway, what matters to us is it's a flow, and it's a flow, and we don't know how much it is. So I'm going to give it a variable. I don't know what flow that is. I'm going to call it U. I'm going to start with U because we're going to need a UV, WXYZ. So that flow comes around here. It's still the same flow when it gets to here. It's still the same flow when it gets to here because it's all the same wire. It's like all the same garden hose. It's all the same flow. Pardon me. Then we get to this junction here where the flow is going to split, and some of it's going to go up this way and some of it's going to go up this way. Now how much is going to go each way? I don't know. We have no idea. So we're going to call that a V. I'm going to call that a W. Two different flows. How much flows is going to depend on how it's interacting with these resistors. That's what these are called, resistors. Resistors are exactly what they sound like. They resist the flow. So a high number means it really resists the flow, and a low number means it just resists it a little bit. So the 6 ohms resists it a lot, and the 3 ohms resists it less. So I'm guessing we'll have more going up the left branch than up the right branch, but it depends on how the whole circuit interacts with itself, really. So anyway, following these flows, let me follow flow V. When I get to this junction here, that's going to split in half, or at least I'm guessing that's what it's going to do. Some of it's going to go that way, and some of it's going to go that way. Now we need to use more letters. So I used a U, V, W. Let's call this one an X. Let's call this one a Y. Now, by the way, I'm kind of guessing that the flow is going to split that way. For all I know, this current goes the other way, or maybe even this current goes the other way. But that's not particularly important when you're playing with algebra, because when you're playing with algebra, all that'll happen is, if it's backwards, if X is backwards, it'll come out to be a negative answer. I love that about algebra. X just means backwards. Or I should say negative just means backwards. Okay. Then over here, we've got one more branch over here, and don't know what that is either, so I'm going to call it a Z. So we've got 6 different currents, U, V, W, X, Y, Z. And then the X and the Z come together again and come out, and they're going to be the same as this current. It's going to be U again, coming around this side. Anyway, those are our currents, and what we would like to do is we would like to solve for them. And in order to solve for them, we need to know a little something else about electricity. There's something called a voltage law. And the voltage law says basically this. In a loop, when you walk around in a circle, in other words, how should I say this? The total change in voltage is 0. It's basically saying you can't walk uphill to school and home. You can't walk uphill both ways. That's what it's saying. So voltage goes up, voltage goes down as you go around a circuit. But if you come back to where you started, the total change is 0. So, like, for example, let's say we started walking here. Let's start here. If I start walking this way, do I see a voltage change? Right here I do. I see the voltage going up by 12 volts. And so I could start writing an equation here. My voltage went up by 12 volts. That's what the V stands for, volts. Now as I come around this way, as I come around this way, well, I can walk whichever way I want. I think I'll take a left and go this way. Now the question is, what's the voltage drop across this resistor? There's another law called Ohm's law that says if you want the voltage drop, you would multiply the 3 ohms times the current, 3V. And since we're going across the resistor, we're losing pressure. Our voltage is going down. See, this is like a pump. A battery is like a pump. It pumps up the pressure. So you pump up 12 volts, and then you lose some over here. You lose 3 times V. You lose it over here. And now if I keep walking this way, I'm going to have another loss of pressure, another loss of voltage. It's going to be a minus 5x. And then if I keep walking, I'll be back where I started. And so the voltage law says that that's supposed to add up to 0. Cool. So that's one of our equations. To get ready to set up a matrix, I guess I would say, what are our variables? U. We have a U, V, W, X, Y, and Z, and then we'll have a constant on the other side. I shouldn't make that line so big. We'll have a constant on the other side of our matrix. So does this equation have any, well, we'd want to rewrite this really. Minus 3V minus 5x equals a negative 12. So we'd have nothing times U, a negative 3 times the V, nothing times W, a negative 5 times the X, nothing times Y, nothing times Z, equaling a negative 12 on the other side. We've just coded our first equation. Since we have 6 variables we're solving for, we're going to have to code 6 equations, so 1 down, 5 to go. Now I'm trying to get rid of this green. Yeah, I'll leave this green because we're gonna walk another circle. We might as well start here again. Come through here. I see plus 12 volts. Plus 12 volts. So I'll call that was equation 1. Now I'm doing equation 2. Plus 12 volts. I come around this way, and maybe I'll go this way instead. So I'm going across a resistor. I'm losing pressure. I'm losing minus, and then you multiply 6 times W. And then you come around this way, come around this way. I'm losing pressure again. That would be a 3 times Z. And then I get back to where I started, so it equals 0. Equals 0. So what have we got here? We've got a negative 6W minus 3Z, and I'd want to put the constant on the other side. And then let's code that. Nothing times U, nothing times V, negative 6 times W, nothing times X, nothing times Y, negative 3 times Z, negative 12 on the other side. Okay, I'm going to walk one more way. I'm going to walk one more way around this thing. Is there another way to walk? Yes, there is another way to walk around this thing. And it's basically start here, come around. Start here, come around. I see the plus 12 volts again. So I'm getting ready to write my third equation. Plus 12 volts. And I'm following the arrows. So I'm going to go this way again. And it's going to be minus 3V. But then I'm going to take a hard right here. Now it's going to be minus, and again, you're multiplying ohms times current. So I'm multiplying 1 times Y. So it's a minus 1Y. Then I have to take a corner and go this way. So then it's a minus 3Z. And then I'm back where I started, right? Yep, then I'll be back where I started again. So that's going to be a 0. Now, let's see. Let's put the negative 3V first. Then the negative 1Y, then the minus 3Z. Put the negative 12 on the other side. Code this equation. Nothing times U, negative 3 times V, nothing times W, nothing times X, negative 1 times Y, negative 3 times Z equals a negative 12. Okay, that's those 3 equations. Now we're going to need 3 more equations. How are we going to get 3 more equations? Trying to erase some of this green stuff here. Okay, we can get 3 more equations by doing what's called the current law. Current law says at any junction, that's supposed to be a J, at any junction, total flow in equals total flow out. Total flow in equals total flow out. So you look at some junctions here. Maybe I'll use a different color this time. Like I might look at this junction. What flows into this junction? Well, this U is flowing into the junction. That's the only thing that flows in. What flows in is the same as what flows out. And what flows out is both the V and the W. So U is equal to V plus W. Or, if I want to put all my variables on the right side, U minus V minus W equals 0. And I can code that equation here. 1 times U minus 1 times V minus 1 times W, no X, no Y, no Z, and it equals a 0 on the right. Let's pick another one of those. How about this one? So at this junction, what goes in is the V. What goes out is the X and the Y. So V is equal to X plus Y. So again, move your variables to the left. It'll equal to 0, and code that equation down here. Nothing times U, 1 times V, nothing times W, minus 1 times X, minus 1 times Y, nothing times Z equals a 0 on the right. And then one more. Oh, we could pick whichever. Let's go to this one. Whoops. Let's go to this junction here. So now what have we got? We got, come on you. We got coming in, we got two things coming in. We get W and Y both coming in. So W plus Y go in, and then what goes out is Z. Put all my variables to the left side and code that equation. W plus Y minus Z. No U, no V. 1W, no X. Did I say plus Y? Plus Y minus Z. Plus 1Y minus 1Z equals a 0. There is our 6 equations with 6 unknowns. And I solved it, and I'm just going to write this down. I got U, V, W. I got 356 over 117. I got 76 over 39. 128 over 117. And then for X, Y, and Z, I got 16 over 13. 28 over 39, 212 over 117. And then I turned these into decimals, and I came up here, and let's see, what would be a good color? How about green? U comes out to about 3.04. These would be called amps. 3.04 amps. V comes out to about 1.95 amps, and this W comes out to 1.09 amps. Notice that 1.95 and the 1.09 really do add up to the 3.04, because the 3.04 comes in, some goes this way, some goes this way, and it all adds up nice. The X came out to, let's see, where's the X? The X is over here. The X came out to 1.23 up here. The Z came out to 1.81 over here. And notice that if you add up the 1.23 and the 1.81, those also add up to 3.04, because that's the 1.23 comes this way, the 1.81 comes this way, they join together and become this 3.04 going this way. So that works, that makes sense too. And the other thing I got was the Y came out to, what is this? This came out to like 0.72 amps coming across the middle here. Okay. Circuits, they're cool. We'll end by taking a rather cursory look at predicting the weather. You've heard the weather guy on, I was going to say on TV. Does anyone watch TV anymore? But you've heard the weather guy say, the models are saying that, you know, whatever, we're going to get really warm tomorrow, or it's going to rain a lot tomorrow. They're always talking about the models. What are these models that they're talking about? Well, I'll give you a rough idea. So to make a model, what you do is you take a map of probably not just the United States, probably a little bit, you know, maybe the world, I don't know, but at least the United States. And you would split the United States up into a whole bunch of little itty bitty cells, you might call them, little parts, little pieces, so that if you zoomed in, what you would see is something like this. You would see, well, let's just zoom in on a little piece like this. So you would have these regions. I don't know how big it would be, a county, I don't know, something like that. But you'd have these small little regions of country. And you'd have maybe call this like a weather station at the middle of each. It'd be a node is what they would call it. And this is where you would have values stored of, say, temperature. So this might be cell number 423, so we'll call that temperature 423. This might be cell 424, so we'll call this temperature 424. This would be temperature 422. And maybe up here you got temperature 523, and down here you get temperature 323. So this is 324, and this is 524, and this is 522, and this is 322, and so on. Anyway, you got all these, you know, every one of these little squares everywhere is a temperature that you need to solve for. What is tomorrow's temperature going to be? Now, if you focus on just this one town or whatever, for now, you'd write an equation is what you would do. You would say the temperature tomorrow will be Well, it's going to depend a little bit on what this temperature is. Your temperature to the west, there's going to be some constant, quote unquote, that they multiply that temperature by. Now, what's this constant going to depend on? It's going to depend on wind speed, maybe humidity, maybe cloud cover, particles in the air from the Canadian wildfires. I don't know. All kinds of things. All kinds of things go into determining that constant. And then it would depend a little bit on this temperature too, so they'd have some different constant times that temperature. And it would probably depend on this temperature too, so they'd have another constant times that temperature. And I bet you it would depend on this temperature too, so they'd have a different constant times that temperature. And then, things that are happening here might be important, so there'd be another constant times, here we are, 423, this temperature. Look at that. So what you'd have is at just for this one locale, you would have, well, the temperatures around you matter, right? So those would enter into the equation, and the temperatures are the variables. These are the things you're trying to solve for. What is going to be the temperature tomorrow? But then these are all your coefficients, and the coefficients have basically physics and stuff going into them. The physics of wind, the physics of rain, the physics of cloud formation, the physics of whatever. Who knows? Like, the sun, the sun, it doesn't give off a constant amount of heat or radiation or whatever you want to call it. It fluctuates, right? There's fluctuations to the sun. All kinds of things would go into those constants. Now, here's the thing. You get that temperature for 423. Notice you've got an equation that involves T423, T422, T4, this has 1, 2, 3, 4. This has 5 temperatures involved. Now, over here, you're going to have another equation for this one, which is going to depend on this temperature, this temperature, this temperature, and this temperature over here. And then over here, you're going to have an equation for this temperature, which is going to depend on this temperature, this temperature, this temperature, this temperature. And every single one of these cells is going to have its own set of constants, potentially. So there's a lot of numbers here. But the thing is, you can just organize all this data into it would be huge. A huge augmented matrix. You have an unknown in the middle of each cell, basically. The temperature in each cell is unknown. And so what do you got? You got 1,000? You got 10,000? How many cells have you got? So you've got, I'm just going to say 1,000. You've got something like in fact, it's got to be bigger than that. I'm going to say it's a 10,000 by 10,000 grid, 10,000 by 10,000 system of equations that you would have to solve. And the cool thing is, in principle at least, we know how they would do that. Now, isn't that cool? Is it going to be accurate? Well, you know how accurate the weather forecast is. Because, it depends on a lot of things. I mean, look at all these, there's an A, a B, a C, a D, and an E for every one of these. There's a lot of constants, there's a lot you have to think about when you say, well, how will the temperature over there affect the temperature over here? So, there's a little guesswork in there, and there's a little repeat, well, I think we can tweak the model this way and it'll work better next year and stuff. There's a lot of continuing work that goes into it. But I guess part of what I want to do is I have 2 things in mind when I give you this example. First is, isn't that cool? You can solve a big giant system of equations to analyze all kinds of things, like the weather, like whatever, right? Climate change, all this kind of stuff. The other thing I would want you to take away is, if someone tries to impress you by saying, the scientific models show, keep in mind that scientific models involve a lot of guesswork. Like I say, there's a lot of guesswork that goes into coming up with what is the real value of A, B, C, D, and E for this locale, and what is the real value of A, B, C, D, and E for that locale, and so on. So it's an art as much as it is a science. But I think that's a good place to end our lecture. Systems of equations, as big as you want them. You can use the computer. It can use Gaussian elimination. There's actually other methods too that you can use to solve these things, but it's cool. So that ends that unit. I guess we should have a test on this stuff now, right? But enjoy this section first because it's really cool to get the solutions out of the computer.